This is the most powerful internal combustion engine on the planet. It stands 44 feet tall, stretches 89 feet long, and weighs over 2300 tons, producing 109,000 horsepower. The Wärtsilä RT-flex96C is the beating heart of the world's largest cargo ships, and the physics of how scientists and designers keep this mechanical monster from tearing itself apart will melt your mind. This is a two-stroke turbocharged diesel behemoth operating in a 14-cylinder configuration. A single cylinder bore is nearly 38 inches in diameter, and the piston travels a massive 8.2 feet up and down with every single stroke. The innovators who designed this had to invent new ways to handle the extreme kinetic energy generated inside the steel block. The rotational force generated by this motion is transferred to a crankshaft that alone weighs 300 tons. That is equivalent of dropping a fully loaded Boeing 747 into the bottom of the structure just to transfer the rotational force to the propeller. But attaching a standard connecting rod directly to a piston of this size would instantly destroy the engine. In normal vehicles, the rod pushes the piston against the cylinder wall, creating side-loading friction. At this massive scale, that friction would melt the metal. To solve this, the designers implemented a crosshead mechanism. The connecting rod attaches to a separate sliding block, keeping the main piston rod perfectly vertical at all times. The piston travels its massive 8-foot stroke with zero side-to-side stress, allowing the machine to run continuously for over 3 years before requiring a major overhaul. But sheer size isn't the most mind-blending part of this machine, it's the combustion. This powertrain doesn't burn refined, clean gasoline. It runs on a heavy fuel oil. This stuff is so thick and unrefined that at room temperature, it basically looks and acts like black tar. To make this tar combustible, the designers abandoned traditional camshafts and implemented a highly advanced common rail fuel injection system. They heat the thick oil until it flows, then send it to a pressurized rail holding the fuel at over 14,500 pounds per square inch. Microprocessors dictate exactly when the solenoid valves snap open, injecting the fuel into the massive cylinders under unimaginable pressure. When the piston travels 8.2 feet upward, compressing that air-fuel mixture, the resulting explosion pushes down with a force of millions of pounds. Yet despite this violent continuous explosion, the machine rotates incredibly slow. It maxes out at just 102 revolutions per minute. Its slow, rhythmic, unstoppable pulse that physically shakes the ocean around it. Because it's a two-stroke design, it delivers a massive power stroke on every single revolution of that 300-ton crankshaft. To feed enough oxygen to a 14-cylinder fire this large, the designers utilized uniflow scavenging. Massive turbochargers force pressurized air through intake ports at the bottom of the cylinder, sweeping the exhaust gases out through a single massive exhaust valve in the cylinder head. This constant unidirectional hurricane of air inside the block ensures maximum combustion efficiency. Operating in this brutal environment requires extreme lubrication. The acidic byproducts of burning low-grade, high-sulfur heavy fuel oil would eat through normal metals in hours. The designers engineered a dual lubrication system, a highly specialized alkaline lubricant is injected directly into the cylinder to neutralize the acid and create a sacrificial barrier on the cylinder walls. Meanwhile, a completely separate high-grade oil lubricates the main bearings and the massive crankshaft. By isolating the systems, the harsh combustion acids are prevented from ever reaching the lower engine components. Power of this magnitude comes with an absolute brutal appetite. If you run the 14-cylinder version at its maximum economy, it consumes roughly 1660 gallons of heavy fuel every single hour. At full load, it burns through over 250 tons of fuel a day. This powertrain operates at a thermal efficiency exceeding 50%. For context, most standard automotive internal combustion engines sit around 25 to 30% fuel efficiency. The scientists who built this machine figured out how to extract every single ounce of kinetic energy from the dirtiest, cheapest fuel on earth. By converting half of the fuel's thermal efficiency directly into forward motion, they ensure that a 200,000 ton cargo ship can carry tens of thousands of shipping containers across the Pacific at over 30 miles per hour without stopping. The modern world doesn't run on the internet or fancy software. It runs on 109,000 horsepower blocks of steel, pushing millions of tons of cargo through open water. It's a testament to what human designers can achieve when they decide to push the laws of physics to the absolute brink. It's a masterpiece of slow, deliberate, industrial survival. But what happens when these exact same laws of physics are accelerated past the breaking point? To see the absolute limit of high-speed mechanical violence, click the video on screen to see exactly what happens inside an engine before it dies in just 4 seconds.